Hello everybody, welcome into another lesson. So today we are going to start a few lesson unit on imaginary and complex numbers. Today we're going to introduce what imaginary and complex numbers are, talk about real world applications of some of those, then I'm going to show you something really cool that's a product of imaginary numbers. But to understand complex numbers in general, it helps to break down sets of numbers. So let's start with, at the very bottom, we have natural numbers. We're going to form a number tree to show you how all this relates. Of course, you have your natural numbers, which are the most restricted set, where those are just your counting numbers, 1, 2, 3, 4, 5, so on. So that's the set of natural numbers. If you go up a little bit, you have what's called the whole numbers. Natural numbers are a subset of the whole numbers, and whole numbers are all your counting numbers plus 0. You can think of it as a whole, like a 0. It looks like a whole. It includes all your natural numbers plus 0. And then the whole numbers are a subset of the integers. In which the integers are all of your whole numbers, including negative numbers. There's still no fractions or anything yet, but integers are all your counting numbers, 0 and negative numbers. And then you have integers, which are the subset of rational numbers. And rational numbers, as we know, are numbers that can be expressed as a fraction. So everything below here, integers, whole numbers, natural numbers, can be expressed as a fraction. But rational numbers, you'll have things like 1/2, negative 1/3, so on. Anything that can be expressed as a fraction. Now, off to the side of that, which is not part of the rational numbers, you have what's called the irrational numbers. So then you have equal to rational numbers are irrational numbers, which irrational numbers, as we know, cannot be expressed as a fraction. So numbers such as pi or any non-terminating repeating decimal that cannot be expressed as a fraction are considered irrational numbers. So the set of rational numbers and irrational numbers together, those are both subsets of the real numbers. The real numbers make up everything listed below. That's the whole set of real numbers. Well, to the side of that, you have what's called imaginary numbers. Imaginary numbers are simply I equals the square root of -1. We're going to delve more into imaginary numbers in a minute. So imaginary numbers, okay? The idea is for real numbers that if you take any number to the second power, you'll never get a negative result. Never. The lowest number you'll get 0. With imaginary numbers, that changes. You have I equals the square root of -1. And we'll delve more to that in a minute. But together, the real numbers and imaginary numbers are both subsets of the complex numbers. And the complex numbers make up everything listed below. Your real numbers and imaginary numbers, both of those subsets are subsets of the complex numbers. So if you ever hear of complex numbers, that's referring to all solutions in both your real and imaginary numbers. So that's how this number tree works. So now we know what complex numbers are. We have an idea what imaginary numbers are. Now let's talk about imaginary numbers. So you have I equals the square root of -1. That's I is denoted to illustrate I it equals the square root of -1, the imaginary unit, the imaginary number. Okay, so here's the million-dollar question. If the numbers are imaginary and not real, why do they even matter? Well, they do have implications in the real numbers, as we're going to see here shortly. Plus, if you're in electrical engineering or anything like that, they explain fluctuations in electrical fields, or they're used in computer programming and design. They're used in quantum physics and quantum mechanics and all kinds of other fields. Plus, I would like to show you all something here. I'm going to turn off my camera for a second. You'll still hear me talk, but watch this. You get something called the Mandelbrot Set. I'm going to write it down. The Mandelbrot Set. I think you're really going to like this. The Mandelbrot Set. Let me turn off my camera real quick here and bring this up. So just give me a second here. Alright, y'all can still hear me? Here's what comes up. That is the Mandelbrot set. Pretty cool, huh? You can plot all those using imaginary numbers for the Mandelbrot set. I don't know if anyone's ever seen that, but that's a product of real and imaginary numbers. Pretty cool, huh? Alright, so let me turn that off here. There we go, back to the lesson. Alright, so the Mandelbrot set involves imaginary numbers. And I definitely can't plot that by hand. You pretty much have to use computer software for that, but I think that's pretty dang cool. So we're going to solve some quadratic equations first to start with that involve imaginary numbers. So now let's say you have x squared equals -4. So you got x squared equals -4. Alright, well, it used to be we would have no real solution, but now we have the whole set of complex numbers, so there is a solution. So like you would if you were solving any other quadratic equation, take the square root of both sides. You'll have the square root of x squared equals, again, plus and minus the square root of -4. So the square root of x squared equals x would equal plus and minus, okay. Now, the square root of -4, can't you break that down into the square root of 4 times the square root of -1? Because 4 times -1 equals -4, right? Well, let's take this a step further. X would equal plus and minus, what is the square root of 4? That's 2. What's the square root of -1? That's I. So what you get is x equals both plus and minus 2i. That is the answer to this. X equals plus and minus 2i. So if you see the square root of -4, you can know that's 2i. Because it breaks down into the square root of 4 times the square root of -1, which would be 2i. So you get x equals both plus and minus 2i. Alright, let's see. So then you have x squared equals -11. So you're given x squared equals -11. So again, take the square root of x squared. set that equal to plus and minus the square root of negative 11, which is going to left side would give you x equals plus and minus. Okay, so negative 11 would break down into square roots of negative 1 times the square root of 11. Well, the square root of 11 is not a perfect square. There are no factors of it that are, but the square root of negative 1 is I. So you could say x equals plus and minus I times the square root of 11. That would be your answer. X equals plus and minus I times the square root of 11. Alright, we have 3x squared equals negative 81. So we're given 3x squared equals negative 81. Well, obviously we want to get the x squared by itself first. So divide both sides by 3, you would get x squared equals negative 27. Now you just take the square root of both sides. So let's see, square root of x squared equals plus and minus the square root of negative 27. So then you'll get x equals plus and minus. Okay. Well, let's start here with factors of negative 27. Definitely we could factor out a square root of negative 1. What else? Now for factors of 27, you have 9 and 3, right? So you'll have a square root of 9 times the square root of 3. So then you'll have x equals, okay, plus and minus, so square root of negative 1 is I, square root of 9 is 3, so x equals plus and minus 3i, then just times the square root of 3. So your two solutions are x equals both plus and minus 3i times the square root of 3. Alright, 2x squared plus 9 equals negative 41. So we have 2x squared plus 9 equals negative 41. Alright, so what we have now is another quadratic equation, but first let's get the 2x squared by itself. So subtract 9 from both sides. If you do that, you'll get 2x squared is equal to negative 50. Now let's get the x squared by itself, so divide both sides by 2. You'll end up getting x squared equals negative 25. And then now you'll just take the square root of both sides, so take the square root of x squared would equal both plus and minus the square root of negative 25. So then x would equal plus and minus, okay, negative 25, you could take the square root of negative 1 times the square root of 25. Well, then x would end up equaling plus and minus 5i. X would equal both plus and minus 5i. Alright, we have 5x squared plus 18 equals 3. Alright, so 5x squared plus 18 equals 3. So get the 5x squared by itself. You would have 5x squared is equal to negative 15. Now get the x squared by itself, divide by 5, you would get x squared equals negative 3. So then take the square root of x squared, set that equal to plus and minus the square root of negative 3. Well, then x would equal plus and minus, alright, square root of negative 3, that could break down into the square root of negative 1 times the square root of 3, which means x would equal plus and minus I times the square root of 3. you could actually write it x equals plus and minus square root of 3 times I. The reason I don't do that, though, is because people can mistakenly end up making it look like the i's underneath a radical sign when it's not. That would be a double square root of I, or double square root of -1, which wouldn't be accurate. So x equals plus and minus I times the square root of 3. All right. We have negative x squared minus 4 equals 14. So negative x squared minus 4 equals 14. We'll get the negative x squared by itself first. So you'll end up having negative x squared equals 18. Then get x squared by itself. You would have x squared equals negative 18. Now just do your square roots. So the square root of x squared would equal plus and minus the square root of negative 18. So then you would get x equals plus and minus. All right. So you can factor out a -1 in your square root. Square root of -1 times, now perfect square of 18 is 9. So you have the square root of 9 times the square root of 2. Which means then that x would equal plus and minus 3i times the square root of 2. So x equals plus and minus 3i times the square root of 2. All right, let's see. 8r squared plus 7 equals 5r squared plus 4. So we have 8r squared plus 7 equals 5r squared plus 4. Well, we definitely need to get the variable term on the left and then just the number on the right. So let's subtract 5r squared from both sides. You would end up getting 3r squared plus 7 equals 4. And then subtract 7 from both sides, you would get 3r squared equals -3. And then r squared would equal -1. So take your square root of both sides. So square root of r squared equals plus and minus the square root of -1, which just means r would equal plus and minus I. So you would simply end up getting r equals both plus and minus I. All right, so let's see. 3s squared minus 1 is equal to 7s squared. All right, so why don't we get the variable term on the left to start with? So subtract 7s squared from both sides, you would get -4s squared. Then move the 1 over. -4s squared equals 1, which would give you s squared equals -1/4. So then just take the square root of both sides. So the square root of s squared would equal plus and minus the square root of -1 over the square root of 4, which means that s would equal plus and minus. So you could write this as 1/2 I. Because 1 times -1 is -1, square root of 4 is 2. So s would equal plus and minus 1/2 I. That would be your solution. So s equals plus and minus 1/2 I. All right, let's see. We have the quantity of t minus 2 to the second power is going to be equal to negative 16. So we have the quantity of t minus 2 raised to the second power is equal to negative 16. Well, again, take the square root of both sides. So the square root of t minus 2 raised to the second power is equal to plus and minus the square root of negative 16. So you'll get t minus 2 on the left is equal to plus and minus. All right, so negative 16 would break down into the square root of negative 1 times the square root of 16, which would mean t minus 2 equals plus and minus. So square root of 16 is 4, square root of negative 1 is I, so t minus 2 equals plus and minus 4i, which means t would equal both 2 plus and minus 4i. So there's your solution. T equals 2 plus and minus 4i. All right, let's see. We have negative 6 times the quantity of u plus 5 raised to the second power equals 120. So negative 6 times the quantity of u plus 5 raised to the second power equals 120. Now, let's go ahead here. Let's get the u plus 5 to the second power by itself. So this would turn into u plus 5 raised to the second power would equal negative 20. Now we'll just take the square root of both sides. So the square root of u plus 5 raised to the second power would equal plus and minus the square root of negative 20. So then you get u plus 5 on the left side would equal plus and minus. Okay. Negative 20 you can break down definitely into the square root of negative 1. Now 20 breaks down into 4 and 5, so you have the square root of 4 times the square root of 5. So then you'll have u plus 5 is equal to both plus and minus. Square root of 4 is 2, square root of negative 1 is I, so plus and minus 2i times the square root of 5. Which would have to mean then that u equals negative 5 plus and minus 2i times the square root of 5. So those are your two solutions. X equals negative 5, both plus and minus 2i times the square root of 5. Alright, let's see. Negative 1/8 times the quantity of v plus 3 raised to the second power is going to be equal to 7. So we have negative 1/8 times the quantity of v plus 3 raised to the second power equals 7. So here's what we got now. We definitely want to get the v plus 3 to the second power by itself, so multiply both sides by negative 8. If you do that, you'll end up getting v plus 3 raised to the second power equals negative 56. Alright, so now let's see. So v plus 3 to the second power equals negative 56. Take the square root of both sides. So the square root of v plus 3 to the second power equals plus and minus the square root of negative 56. So then you'll have v plus 3 is equal to plus and minus. Okay. So square root of negative 56, of course you have the square root of negative 1 as a factor. Now you also would have 4 and 14 are factors of 56, so the square root of 4 times the square root of 14. And 14 doesn't break down any further. So you're left with v plus 3 equals plus and minus. Square root of 4 is 2. Square root of negative 1 is I. So plus and minus 2i times the square root of 14, which would mean v equals negative 3 plus and minus 2i times the square root of 14. So v equals negative 3 plus and minus 2i times the square root of 14. One more of these, and I'm going to talk about the cycles of I. So we have 9 times the quantity of W minus 4 squared plus 1 equals 0. So 9 times the quantity of W minus 4 squared plus 1 equals 0. Well, let's get 9 times W minus 4 squared by itself to start with. So this is going to look like 9 times the quantity of W, that's minus 4 squared, would equal negative 1. Now let's just get the W minus 4 squared by itself. So that would be W minus 4 squared would equal negative 1/9. Now we'll just take the square roots of both sides. So the square root of W minus 4 raised to the second power would equal both plus and minus the square root of negative 1 over the square root of 9. Alright, so then you'll have W minus 4 on the left-hand side would equal plus and minus, okay, so this would be plus and minus 1/3 I. So then W would simply equal 4 plus and minus 1/3 I. And that would be your solution. Really two solutions. W equals 4 plus and minus 1/3 I. Alright, we're going to talk about cycles of I real quick. So, if you have I, that equals the square root of negative 1, right? That's the same as I to the first. Well, what about I to the second? What if we did I to the second? So, that's going to be the same as the square root of negative 1 raised to the second power. Well, what do we know about square roots raised to a second power? It simply cancels out the square root, but you keep what's under the radicand. So the square root of I squared equals negative 1. So now you're beginning to see how imaginary numbers can have implications in the real number systems. If you square I, you get negative 1, which we know is a real number. Okay, so what about I to the third? I to the third is the same as I to the second times I, right? Wouldn't it be the same? So we already know I squared is negative 1. That'd be the same as negative 1 times I, or just simply put, would give you negative I. So I to the third is the same as negative I. Now what about I to the fourth? I to the fourth, isn't that the same as I squared times I squared? Well, what was I squared? That's negative 1. Then you'd have times another negative 1. Negative 1 times negative 1 is positive 1. So I to the fourth turns into positive 1. If you're wondering what I to the 0 is, it's just 1. I to the 0 is 1. That would still be a real number 1. Now, here's where it gets interesting. What if I gave you I to the fifth? I to the fifth is the same as I to the fourth times I, right? Well, I to the fourth was 1, right? And then you just have 1 times I. That would just be back to I. So, I is cyclic in the sense that for every 4 powers, it repeats the pattern. So, let's say I gave you I to the 8th. How would you handle I to the 8th? Here's a test for it. You're going to take I to whatever power. We'll call it the A power. If A divides evenly by 4, treat the power as I to the 4th. So we have I to some arbitrary power. If A divides evenly by 4, treat the power as I to the 4th. So I to the 8th. You'll take that 8th power, divide it by 4. Does it divide evenly with no remainder? Yes, it does. You get exactly 2. So I to the 8th would be exactly the same as I to the 4th, which would just give you 1. Let's try I to the 12th. Does 12 divide evenly by 4? Yes, 3. It divides exactly 3 times with no remainder. So this is also the same as I to the 4th. That would equal 1. How about I to the 100th? What if I took I to the 100th power? Well, does 100 divide evenly by 4 with no remainder? Yes, it's exactly 25. So this would be the same as I to the 4th, which would give you positive 1. Okay? That's great. Now, we've seen those. What about if we have remainders? So, for example, I'll give you I to the 9th. What about I to the 9th? If A, alright, so let's say, let's take 9 divided by 4. What is 9 divided by 4? Well, that's going to be what? 2 1/4, right? 9/4 is the same as 2 1/4. What you do, again, we still divide by 4, but how it behaves, you just take the remainder. You have a remainder of 1 for 2 1/4, right? So I to the 9th would behave as I to the 1st, which would just simply be I. So I to the 9th is the same as I, because when you take 9 and divide it by 4, you have 2 1/4, which means you have a remainder of 1. So that's what you go by. Now this time, let's say I give you I to the 10th. Well, take 10 and divide it by 4. 10 divided by 4, that's going to be what? 2 2/4, right? Yes, I know you're saying, wait, we can reduce that to 2 1/2. When you're dealing with the cycles of I, don't reduce your fraction, just leave it be. This 2 2/4 means you have a remainder of 2. If you have a remainder of 2, that means that the I to the 10th will behave as I to the 2nd, which would be -1. So I to the 10th would behave as I to the -2nd, which would be -1. And then if I take, well, let's take I to the 11th. So let's take 11 divided by 4. 11 divided by 4, that's 2 3/4, is it not? 11/4 is 2 3/4. Well, your remainder is 3. If your remainder is 3, that means it's going to behave as I to the 3rd, which would just give you -I. So you're always going to, if you have any power of I greater than 4, divide by 4, whatever your remainder is, it's going to be the same as whether it's I to the first, second, third, or if you have no remainder, and it divides by 4 evenly, it behaves as I to the fourth. So let's say, heck, let's go for broke. I to the 250th. We have I to the 250th. So let's take 250 divided by 4, right? So let's see, 250 divided by 4. So that's going to give you, of course, so 125. That would give you 62 and 2/4. You end up getting 62 and 2/4. We don't care about the 62. We only care about that remainder of 2. That remainder of 2 is what we care about. Excuse me. So I to the 250th would equal I to the second, because you have that remainder of 2, which would give you -1. So if you're ever asked to find I to the 1,000,000th, divide by 4, and it just recycles powers 1 through 4. And if you have a remainder, if it doesn't divide by 4 evenly, that remainder is the power of I that it behaves as, whether it's 1 through 3 or 4. So that's it for this lesson. Now you can see how imaginary numbers can have implications in the real numbers. So that's why they're important, and fluctuations in electrical fields and all kinds of other things. So next lesson we will talk about plotting numbers in the complex plane, and we'll do the standard form of a complex number and some simple addition and subtraction with them. So I hope everyone has a great day. Take care.